All right, I'm gonna keep going. Last time I had written this some ASM, some assembly here. Didn't really understand I sort of understood what some of it was doing. I figured out like one of these ones meant like standard out, and you were writing this to standard out, and is anyway. Hopefully, this section, which was next, was supposed to describe it. The next session will explain this sample program in greater detail. So we're hoping that we're going to get a greater understanding of this code right here. Okay. Um. Oops. Okay. Hopefully you can see that. Let me take out my AirPods. Okay. As we remember from the von Neumann machine description, there's only one memory for both code and data. Those are indistinguishable. However, a programmer wants to separate them. An assembly program is usually divided into sections. Each section has its use. For example, .text holds instructions, .data is for global variables, data available in every moment of the program execution. One can switch back and forth between sections. In the resulting program, all data corresponding to each section will be gathered in one place. To get rid of numeric address values, programmers use labels. They are just readable names and addresses. They can precede any command and are usually separated from it by a colon. There's one label in this program at line 5, _start. Line 5? That's not line 5. This is line 7 and this is line 1. I'm not sure which one he's talking about. Line 5 doesn't have anything. 1, 2, 3, 4, 5. Okay, well I think it's this label. This can be anything I want, maybe. Sorry, I'm a little bit sick still. A notion of variable is typical for higher level languages. In assembly language, in fact, notions of variables and procedures are quite subtle. It is more convenient to speak about labels or addresses. An assembly program can be divided into multiple files. One of them should contain the _start label. It is the entry point. It marks the first instruction to be executed. This label should be declared global. See line 1, global start. Okay. The meaning of it will be evident later. Perfect. Okay. Comments start with semicolon and last until the end of the line. I like that. It's nice. Assembly language consists of commands which are directly mapped into machine code. However, not all language constructs are commands. Others control the translation process and are usually called directives. In the Hello World example, there are 3 directives: global, section, and DB. That is this, and this, I suppose. Note, assembly language is, in general, case insensitive, but label names are not. MOV, M, big O, big V, and big M, OV are all the same thing, but global start and global start are not. Section names are case sensitive too. Section.data and section.data little data differ. Okay, the DB directive is used to create byte data. Okay, data of bytes maybe stands for, not database. Usually data is defined using one of these directives, which differ by data format. DB means bytes, ddub means so-called words, 2 bytes each, dd means double words, 4 bytes, dq quad words, 8 bytes. Okay, let's see an example in listing 2.2. Okay, so it has another section data, which I guess it's kind of like this data here. It says example 1 is bytes 5, 16, 8, 4, 2, 1. Example 2, times. I don't know what times is. 909. Something here. ddub is 2 bytes, 909. The NASA manual. Okay, we go. Times n command is a directive to repeat command n times in program code. Oh, so we're doing db 42 999 times, I guess. If you copy paste it n times, as if you copy and paste it n times. Okay. It also works with central processor unit instructions. Note that you can create data inside any section, including .txt. .text. As we told you earlier, for CPU data and instructions, For a CPU, data and instructions are all alike, and the CPU will try to interpret data as encoded instructions when asked to. These directives allow you to define several data objects one by one, as in listing 2.3, where a sequence of characters is followed by a single byte equal to 10. All right, message DB, that's what we have here. These directives allow you to define several data objects one by one, as in listing 2.3, where a sequence of characters is followed by a single byte equal to 10. That's why the comma is here. So let's see, you're doing several things, which is why this was 5 and then 16 and then 8 and then 4 and then 2 and then 1. Okay, got it. Letters, digits, and other characters are encoded in ASCII. Programmers have agreed upon a table where each character is assigned. It's just ASCII. Okay, we start at address corresponding to the label message. We store the ASCII codes for all letters of string hello world. Then we add a byte equal to 10. Why 10? By convention, to start a new line, we output a special character with code 10. So is 10 equivalent to like what you'd see this as probably? Okay. Terminological chaos. It is quite common to refer to the integer format most native to the computer as machine word. As we are programming a 64-bit computer, where addresses are 64-bit, general purpose registers are 64-bit. It is pretty convenient to take the machine word size of 64 bits or 8 bytes. In assembly programming or Intel architecture, the term word was indeed used to describe a 16-bit data entry because on older machines it was exactly the machine word. Unfortunately, for legacy reasons, it is still used as in old times. That's why 32-bit data is called double words and 64-bit is referred to as quad words. That is confusing. Okay. 223. Basic instructions. The mov or move instruction is used to write a value into either register or memory. The value can be taken from other registers or from memory, or it can be an immediate one. However, move cannot copy data from memory to memory. The source and the destination operands must be of the same size. Okay, so it can move from memory to a register, or register to memory, or I guess register to register, but it can't move memory to memory. And the things, source and destination, need to be the same size. Okay. The syscall instruction is used to perform system calls in star Nix systems. The input-output operations depend on hardware, which can be also used by multiple programs at the same time. So programmers are not allowed to control them directly, bypassing the operating system. Okay. Each system call has a unique number to perform it. The RAX register has to hold the system call's number, which is why we stuck 1 in here, hence this comment. The following registers should hold as arguments. RDI, RSI, RDX, R10, R8, and R9. Okay. It seems arbitrary for now, but maybe it'll clear up later. System call cannot accept more than 6 arguments. Oh, is that like the order of its arguments? Like argument 1 goes in RDI, which is why we stuck argument 1 in RDI. Look at that. If there wasn't, oh look, argument 2 in RSI. See that? Okay. Argument 3 is in RDX. If we needed an argument 4, we would have stuck it in R10. Gotcha. Did I make like a nice screenshot of that table? Looks like I deleted it. Okay. Execute syscall. Okay, so you stick the call number in there, and you stick the arguments in there, and then you execute it with syscall, which doesn't take any arguments because you already stuck them in these registers. Cool. Okay. It does not matter in which order the registers are initialized. Note that the syscall instruction changes RCX and R11. It does? We'll explain the cause later. Okay. When we wrote the Hello World program, we used a simple write syscall. It accepts 1, the file descriptor, which is this rax 1. Oh yeah, this standing out was 1. No. Okay, the buffer address. We start taking consecutive bytes for writing from here. Okay. The amount of bytes to write. Maybe these aren't in order. The amount of bytes to write. Okay. To compile our first program, save the code in hello.asm. Oh, perfect. This is fun. It's already saved in hello.asm. Could I like shrink this down a little bit? Oops. Oh no. Oh yeah, perfect. Okay. Shrink it down a little bit and make that smaller so we can see all of it. Alright, to compile our first program, save the code in hello.asm and then launch these commands in the shell. Let's try. We do like down here. Oops, not there. Here. Okay. We'll go. Do I have it here? Okay, perfect. NASM, which we have, not MASM, NASM dash felf 64. Hello.asm. And then as output, I guess is what this means. We'll do hello.o. Wow, I was not expecting that to work. Okay, it worked. Hello.o. And then LD, which I think is the linker. Man, LD. It's a linker. Check it out. LD dash O, not 0, dash O. Hello, hello.o. Uh-oh. Platform not specified. Arch not specified. No platform inversion specified on command line. Ignoring file hello.o. Building for unknown but attempting to link with file. Oh dear. Okay, this is not what I was hoping for. And then you can chmod it, but we don't even have a thing to chmod. So, details of compilation process. Hello world, and then segfault. All right. Well, I need to figure out how to build. Let's ask the Google. How to run x64 assembly on Apple Silicon. It looks like I already looked at this. Running ARM, how to set up ARM. How to hello world ARM. That's for ARM. How to emulate Apple Rosetta. Isn't this? Oh wait, Rosetta, not Rosetta Stone. Apple Rosetta. This. I don't install Rosetta. Is it like a CLI or how do I do this? Let's ask ChatGPT. Okay. Let me pull it back up here. Okay, this guy. How? Blow it up so you guys can see. How? Okay, wait. So look, I have some what is it? 86 underscore 64 ASM code that I whipped up. I want to run it. I am getting linker. Okay. I'm getting linker errors, I think, because I'm on Apple Silicon, which is ARM. Maybe I should show you the error I'm getting in particular. What was it? It's this, no? Okay. Help. I was told that I could use Rosetta. Alright, the error message you're seeing are related to the fact that you're trying to link x64 assembly code on our machine without specifying the correct architecture. Okay. Rosetta 2 allows you to run this. That's what I thought on Apple Silicon. You can use it to run those apps, but you need to ensure that your build tools are also running under Rosetta. Specify the architecture. When you're assembling and linking your code, you need to specify the architecture explicitly. Okay. You can do this by using the arch flag. That's what the arrow was saying, wasn't it? Specify the platform. Use the platform version flag to specify the platform and its version. Okay. Here's a step-by-step guide to compile and link your x86 assembly code on Apple Silicon. Assembly code. Use AS. Oops. Sorry. Use AS to assemble your code. Stop it. Okay. With a arch. And then link like that. Okay. This is a little more complicated. Run the code with Rosetta. arch command. Okay. All right, we'll just try these steps, I guess. See what happens. Arch. Well, first let's clean up what we did. Okay, so hello.o. Oh look, I've done this before. Okay, dash arch. That's x80, 86, 64 dash o. Pardon my cough. Let's see what this does. Yeah, that's what I thought. Okay. Hey, these are the same as the errors I was getting with LSP. Okay, let's try NASM. What is NASM? So I can't use NASM. Make sure to specify that. Okay. Okay, this is a little different. NASM dash F macho 64 dash O hello. No, dot O hello dot as. Ooh, that worked. Now I'll do link dash arch x86 64 platform version Mac OS. Wait, I'm not on Mac OS 11. Should those 11.0.0 be replaced? Oh, you guys can't see this, it's behind my head. Okay, be replaced with my current Mac OS version. It's good practice. What is my current Mac OS version? 15.3.1. 15.3.1. Said it twice for some reason. Dash O hello dot O dash L big S system. There's no way this is gonna work. Yeah. I need to code x86 assembly for my semester drive. I'm on a MacBook Pro, perfect, which have an ARM processor. I saw it on YouTube that I can write ARM version assembly on MacBook, but is it possible to code x86 assembly on MacBook? If so, then what is the actual process to do it? It's very simple using Rosetta 2. Oh, perfect. He's a real person. Okay, this is like perfect. This is perfect. Okay, let's try it. Let me get rid of the object file I made. Okay, arch, yeah, I'm on ARM64. Okay, and then you try arch dash x86. I don't know why it's so hard for me to type. 64. GCC. Okay, and then hello.asm. He is .s. Okay, dash O hello. I guess. No. It's doing something. It's thinking. And these are, again, those same errors I was getting with the LSP. See, why does he have that leading dot global? This guy didn't have it. He says global start with no dot. Very confused. Surely it doesn't have to do the fact that this is that and not that, right? Try it again. But that. No, it's the same thing. That's what I thought. Okay. Oops. Look, if I change this to dot global, is it gonna be happy? No. It's happier. Now it's tripping on section and message. Oh no, it's not. It's actually tripping on section. Let's try that. It's tripping on the other section. Single quote way too long. What? Is this supposed to be double quote? Seems like almost like I'm writing like a different. See, that syntax highlights correctly too, and this doesn't. Something funny is going on. Something funny's going on. Okay, let me start like a new chat here. I have the following x86 sorry, x64 assembly code. Looks like this. I'm trying to run it on Apple Silicon using this, what's the command? This guy. Okay, copy him. And I'm getting lots of errors, and we'll put the errors in here too. The errors look like all of this, no? Help! Trying to... The errors you're encountering are due to the fact that you're trying to assemble x86-64 assembly code using a toolchain that doesn't recognize the syntax. The GCC command you're using is not suitable for assembling raw assembly code directly. Instead, you should use an assembler like NASM to compile the assembly code into an object file, then link it using GCC. Here's how you can do it. Install NASM. I already have NASM. Assemble the code. Use NASM to assemble your code into an object file. Run the following command. Okay, this is encouraging because it's sort of what this guy was saying. Let's try this again. Okay, NASM-F macho. This is like a totally different command than he was. Okay, well, let's try it. Hello. Okay, and then link the object file gcc -o hello.o. See, look, found architecture x64, required architecture ARM64. That's what I thought. But what if we do, now, what are this guy's linker? This. LD-O, this. Platform version. I don't know how to do that. What can I use LD? I'm pretty doubtful of this. So this is the same. This is different and new. All right, let's try it. LD-O hello. We're gonna do hello.o -L system -Mac OS X underscore version underscore min 10.13 -E underscore start. Has been renamed. Huh, that's kind of actually a helpful error. System, library system not found. It says that. Indicates the linker is unable to find the system library which is necessary for linking your program on macOS. This can happen if the library paths are not correctly specified. To solve this, you can specify the path to the system libraries explicitly. I already did that. Okay, is that where my CD library, what is it? Developer, command line tools, SDKs, Mac, osx.sdk, user lib? It's at least a real place and there's all this stuff in it. Whole bunch of stuff in here. Check it out. Swift. Okay. So we go LD-O hello hello.o -L system, and then we pass it library developer command line tools SDKs Mac OS X .SDK user lib, and then Mac OS got renamed to just Mac OS version min 10.13 -E underscore start. Very doubtful. Illegal text relocation in underscore start to message. Okay. Now it says this. Common issue when dealing with assembly code on macOS, especially when using that Macho 64 format. To solve this, you need to ensure that your data section is properly aligned and that your using position independent code. Here's how you can modify your assembly code and the build process. Modify the assembly code. Oh dear, I don't really want to modify my assembly. We'll try it. Okay, test.asm. Here's what this guy is suggesting. This. What did he actually change? Use this as Leah. Use Leah RSI rel message to load the addressing message in a position independent way. Correct syscall numbers for macOS. Oh, they're different. Assemble and link. Use NASM and LD as before. So let me do this. Okay, so that's NASM-F macho. Same as here, but this is now test. And this is now test. Now we have a test.o right here. Okay. And then this linker command, which we need to edit. Like this doesn't have an X. And this now is test. Whoa. Would you look at that? There's actually binary. Ta-da! Okay. That's all very well. But I'm not sure about how I had to like change all this. Like the syscall numbers changed. There's this weird line that I do not understand. There's two syscalls, and there's this XOR, like that's the exit code or something. Oh, so what? This is the print, and this is like for exit. Huh. Just a little bit skeptical. All right, I'm a little late this morning, so I'm actually gonna stop here. If any of you have any input on like if this is the right process for running x64 assembly on Apple Silicon, or if there's a better way. I mean, this obviously works, but I'm not sure if I'd know how to like. I'm sure I figured it out, but like if I'd have to change all of his assembly examples to use like these and all that kind of stuff, or I don't know if there's a better way or not. If you know, let me know. Yeah, until tomorrow.